Welcome to the lecture series of Abstract Algebra, Part 3 of Module 1. It's me, Dr. Shahida Yeti, Assistant Professor, MES Mampad College. Before starting this session, I have a suggestion for you. You should watch the Part 1 and 2, then only you can understand what I am going to explain here. For reference, you can use the book A First Course in Abstract Algebra by John B. Fraley. Today we are going to discuss about the concepts, groups and elementary properties of groups. To define a group, we should know what is a binary structure. That is, a binary structure is a set, a non-empty set, and an operation star. Here also, for group, we consider a non-empty set G and operation star, which satisfy three axioms as listed below. That is, the definition of group is a group G star is a set G closed under a binary operation star, such that the following axiom satisfies. First one is associativity of star. That is, if we take any three element from G, then we have A star B star C is equal to A star B star C. Second axiom is existence of identity. That is, there exists an element E belongs to such that for any other element A belongs to G, E star A is equal to A star E is equal to A. Third one is existence of inverse. That is, corresponding to each element A belongs to G, there is an element B in G such that B satisfying this property A star B is equal to B star A is equal to E. Here the element B is called the inverse of A. That is, the element B which satisfying the property A star B is equal to E is equal to B star A. Then B is said to be the inverse of A and is denoted by A inverse. That is, more clearly we can say that A star A inverse is equal to A inverse star A is equal to E. Next one is abelian group. A group G star is said to be abelian or commutative group which satisfy additional property 4. That is the property that if we take any two elements A comma B belongs to G, then A star B is equal to B star A. It's a problem. Here we consider the set Z of integers. That is the set of all elements etc. minus 3, minus 2, minus 1, 0, 1, 2, 3, etc. Now Z is a abelian group with the operation addition. So we want to check Z satisfy, under addition Z satisfy four properties. First one is the closure property. That is, if we take any two element from Z, then adding this element, the sum must be in Z. This property is trivial because if we take any two integers and add them together, then the resulting element must be an integer. And second property is associative property, as we mentioned in the previous slide. That is, if we take any three integers A comma B and C, then A plus B plus C is equal to A plus B plus C. Third one is we want to show that there exists an element, identity element, which satisfies the property that E plus A is equal to A is equal to A plus A. Here the identity element is 0 because if we adding any element integer to 0, the result must be the same integer. Next property is we want to find the inverse of A. That is, we want to find an element B such that A plus B is equal to 0. Then that B must be minus A. That is, for every A belongs to Z, minus A is the inverse of A. And finally, we want to show that Z under addition is an abelian group. To prove the property commutativity or the abelian property, if we take any two integer A and B, then A plus B is equal to B plus A. Hence, Z plus is an abelian group. Second problem. The set Z plus of natural numbers, that is the set of all positive integers, is not a group with respect to addition. What is the reason? We can easily verify that Z is closed and with respect to operation of addition. That is, if we add any two natural number, the resulting number must be a natural number. And the second condition is satisfied. That is, associativity satisfied in Z plus. That is, if we take any three numbers a comma b comma c in Z plus, then a plus b plus c is equal to a plus b plus c. That is, the associative property is also satisfied in Z plus plus. Then which property is violated? We cannot find an identity element E such that E plus A is equal to A is equal to A plus A, because 0 is the additive identity, but the 0 does not belong to set of all positive integers. Therefore, set of all positive integers under addition is not a group. In the problem 3, here we consider a MZ, that is M multiple of set of all integers. Now we want to prove that this is an abelian group. We want to prove that this set G is closed under addition. Second one is this set G is satisfy the associative property. Third one, we want to find an identity element, and third, for any element in G there exists an inverse. Okay, so let me take two element a comma b belongs to the G. Then A is of the form some Rm and B is of the form Sm. Adding two numbers, we get A plus B is equal to Rm plus Sm. That's equal to R plus S into M. Here R and S are integers, then R plus S is again an integer. So we get R plus N plus S into M belongs to G. Therefore, addition is a binary operation on G. Now we want to prove that addition is associative in G. For any three elements ABC, A plus B plus C is equal to A plus B plus C in G. And also 0 belongs to G. 0 seems to be 0 multiple of M, that's equal to 0. And 0 plus A is equal to A plus 0 for all A belongs to G. Therefore 0 is an identity element. Now it's only remain to, now we want to prove that for any A belongs to G, A is of the form Rm for some integer R, then minus A is equal to minus Rm, that's equal to minus R into M. It also belongs to G because minus R is an integer. Also A plus minus A is equal to what we get, Rm plus minus R into M. Taking M outside, we get R minus R into M, that's equal to 0, M is equal to 0. So 0 belongs to M, therefore minus A belongs to G. That is, if we take any element, then its additive inverse is also belongs to G. The last one is we want to prove that G is an abelian group. That is, if we take any two element A and B, then A plus B is equal to B plus A. Therefore, G plus is an abelian group. Problem number 4. In this problem, we consider the set of all n by n non-singular matrices having their elements as rational numbers. Now we want to show that this is a non-abelian group with matrix multiplication. So here M be the set of all n by n non-singular matrices, and the entries of the matrix elements are rational numbers. And we know that product of any to n by n non-singular matrix is non-singular. M is closed under the operation multiplication. And also In denote the n by n unit matrix, that is In is equal to the matrix 1 0 0 0 etc 0 0 1 etc 0 etc etc in the nth row 0 0 0 etc 1. That is In is the matrix which only non-zero elements in the diagonal, and the diagonal entries are 1. Then In acts as an identity element here. That is In into A is equal to A is equal to A into In. Therefore In is the identity element for the composition. And also here M elements of M are non-singular matrices of order M by n. We know that every non-singular M by n matrices is invertible. Therefore for any element in M there exists an inverse. But the metric multiplication is not commutative. This group is non-abelian. Think about set of all rational numbers is not a group under the operation of multiplication. Why? Finite group and group table. A group G consisting of finite number of elements is called a finite group. Otherwise, the group G is called infinite group. For example, if we consider the group table given below, in the first table there is only one element. The element must be identity, then only it satisfies the property of a group. That is, here only element is the E star E is equal to E. Here the inverse of E is E itself. The second table, star is a binary operation defined like this, and the elements of the second table are E and A. Here E is the identity and A is a non-identity element. Here the inverse of A is equal to A itself. If possible, the inverse, assume that inverse of A is equal to E, then what happen? A become identity itself. That is not possible. Therefore, the inverse of A must be A itself. And in the third table, here there are three elements E, A, B. The inverse of E is equal to E itself, and inverse of A is equal to B, and inverse of B is equal to A. If possible, we assume that inverse of A itself, or inverse of B is B itself, then what happen? A or B become the identity, which is not possible. In this example, we Z6, the set 0, 1, 2, 3, 4, 5 with addition modulo 6. In this step, this is an abelian group, finite abelian group of order 6. Elementary properties of a group. First theorem, uniqueness of identity and uniqueness of inverse. The theorem says that if the identity elements exist in group, that must be unique, and the inverse exists in the group must be unique. The statement is like this: in a group G with binary operation star, there is only one element E in G such that E star X is equal to X is equal to S star E for all X belongs to G. Like for each A belongs to G, there is one and only one element A dash in G such that A dash star A is equal to E is equal to A star A dash. Here A dash is said to be the inverse of A. The proof is like this. Here we consider E as the identity element, G star be the group. Choose an element A belongs to G. Suppose A has two inverses, say A dash and A double dash. We get A star A dash is equal to identity is equal to A dash star A. Similarly, A star A double dash is equal to E is equal to A double dash star A. Then A dash is equal to A dash star A. Instead of star, we substitute A star A double dash. Then we get A star A double dash, that's equal to E star A double dash, that's equal to A double dash. And here we started from A dash and reached A double dash. The remaining thing is we want to show that the identity element must be unique, because by the definition of the group G, the identity is always unique. Second theorem, let G star be a group and A is an element of G. The inverse of A is A inverse. Then we want to show that inverse of A inverse is A itself. That is, A inverse all inverse is equal to A. Let E be the identity element of a group G. Then by the definition of inverse, we have A star A dash is equal to identity, that's equal to A dash star A. Also, A belongs to G implies A dash belongs to G. Let A dash all dash be the inverse of A dash. Now A dash all dash star A dash is equal to A. E implies A dash all dash star A dash star A is equal to E star A. That is, finally we get A double dash is equal to A. That is, A is the inverse of A dash. Third one is reversal law. Let G star be a group. For any A comma B belongs to G, the inverse of A star B is equal to B star B inverse star A inverse. That is, A star B all dash is equal to B dash star A dash. The proof is like this. Let E be the identity element of a group G. A and B are any two elements of G. Then since G is a group, A dash and B dash also are belongs to the same group G. Now A star A dash is equal to E is equal to A dash star A. Also B dash star B is equal to E is equal to B star B dash. Here dash denote the inverse. Now we want to prove that the inverse of A star B is equal to B inverse star A inverse. That is, taking the star of these two elements A star B star star A dash is equal to E. We want to prove that A star B dash star A dash is equal identity. From this calculation we can easily verify that A star B dash star A dash is equal to identity. Similarly, B dash star A dash star A star B is equal to E. Hence, A star B dash star A dash is equal to identity. That's equal to B dash star A dash star A star B. Therefore, the inverse of A star B is equal to B inverse star A inverse. Fourth theorem is cancellation laws. If we consider three elements A, B, C in a group G, then the left cancellation and right cancellation will hold. That is, A star B is equal to A star C implies B is equal to C, and B star A is equal to C star A implies B is equal to C. Let E be the identity element of the group G. Then by the existence of inverse we have A belongs to G implies its inverse also belongs to G, and A star A inverse is equal to identity is equal to A inverse star A. Now A star B is equal to A star C implies starring A inverse in both sides, we get A inverse star A star B is equal to A inverse star A star C. Using the associative property, we can regroup it as A star A inverse star B is equal to A inverse star A star C. Here A star A inverse is equal to identity. Therefore, E star B is equal to E star C, which implies B is equal to C. Similar way, we can prove that the second cancellation law. Theorem 5. If A and B are any two elements of a group G star, then the linear equation A star x is equal to B and Y star A is equal to B have unique solution x and y in G. So first we want to show that there exists a solution, and secondly solution must be unique. For the first part, consider an element A belongs to G. A belongs to G implies its inverse also belongs to G. And taking A inverse belongs to G and some other element B belongs to G, A inverse star B also belongs to G. Now consider the equation A star x is equal to B. Instead of x we replace A inverse star B. Then what we get? A star A inverse star B is equal to A star A inverse star B. That's equal to A star B is equal to B. Hence, x is equal to A inverse star B is a solution of the linear equation A star x is equal to B. Now we want to prove that this solution must be unique. To prove the uniqueness, if possible, we assume that there exists more than one solution. And if possible, assume that there exists two solutions, x is equal to x1 and x is equal to x2 for the given linear equation A star x is equal to B. Then A star x1 is equal to B and A star x2 is equal to B. Now, which implies A star x1 is equal to A star x2. Then from left cancellation law, we get x1 is equal to x2. Hence, the solution of the given linear equation A star x is equal to B is unique. So, the similar way we can prove that B star A dash is the unique solution of the equation Y star A is equal to B. Problem number 1. Show that if every element of a group G is its own inverse, then G is abelian. Here we want to prove that G is a group with the property that every element of G is its own inverse. That is, if we take any element A belongs to G, then A inverse is equal to A. then G must be, we want to prove that G must be abelian. So here we consider the group G star having this property, and let A and B are any two elements of G. Now we want to prove that A star B is equal to B star A for any AB belongs to G. Then A star B, since G is a group, A star B is also an element of G. A inverse is equal to A, B inverse is equal to B, and also A star B inverse is equal to A star B by the given property of G. Now A star B whole dash is equal to A star B, which implies A star B whole dash is equal to reversal law, that is B dash star A dash, that's equal to A star B, which implies what is B inverse? B inverse is equal to B and A inverse is equal to A. Therefore, A star B is equal to B star A for all AB belongs to G. Therefore, G is abelian. Next problem is, show that if G is a finite group with identity E and with an even number of elements, then there is an element A not equal to E in G such that A star A is equal to identity. So the property of group is like this. G is finite group. G contain even number of elements. Now we want to prove that there exists a non-identity element A which having the property that it has its own inverse, that is A star A is equal to identity. Let G be a finite group with identity E with an even number of elements. Since G is a group, every element of G has inverse, and the inverse element is also belongs to G. Thus, n element and their n inverse together 2n elements in G. Out of these 2n elements, E has its own inverse. Thus, we have only 2n minus 1 elements. If possible, let there does not exist a non-identity element A in G such that A star A is equal to E, then what happened? G has only 2n minus 1 elements. This is not possible. Therefore, G must contain a non-identity element A which satisfies the property that A star A is equal to identity. That is a self-inverse element. So thank you for watching this video, and if you have any doubt, contact with me. Thank you.